In the last class, we looked at the Mach cone and the propagation of disturbances from an object which was moving with speed greater than speed of sound. So, this is the point disturbance which moves with the speed which is greater than the speed of sound, and these are the spherical wavefronts of sound waves which were generated at an earlier instant in time. Okay. And as you can see from this triangle PQR, you can see that the radius of this triangle, so this is drawn after an instant delta t, after a time interval of delta t. So, in a time interval of delta t, this disturbance propagates a distance a times delta t, as you can see from here, and in that same interval of time the object would have travelled a distance equal to u times delta t. So that the angle, semi-vertex angle of the cone mu is going to be nothing but u is going to be, a over u, which is then equal to sine inverse 1 over m. So from the triangle PQR, from triangle PQR in this figure, we can see that sine mu is equal to a delta t divided by u delta t. So that is 1 over m. So that mu is arc sine 1 over the Mach number, and this mu is called the Mach angle. Note that mu is not the flow deflection angle in this case. The flow is deflected through a very small value, much smaller than mu. So mu is the semi-vertex angle of the Mach cone. Okay, so this is the other point that I want you to note from this diagram is that the point R, if you look at point R, notice that the wavefront here, any point here where the surface of the cone is tangential to this, notice that the surface of the cone is tangential to the spherical wavefront at any point, as you can see from here. So the angle here is 90 degrees. We have already made use of that in defining or in evaluating the Mach angle. So this is 90 degrees. So which means that the spherical wavefront expands this way with velocity equal to a. So that means if you look at the Mach wave is the surface of the cone. So the velocity component normal to the surface of the cone is equal to speed of sound a, right? And we can also see that there is a flow which approaches this way. If you look at an observer sitting at point R, he perceives the flow to approach him with a supersonic speed in this direction from left to right, because the object itself is moving right to left and it is dragging the cone along with it, right? The object is dragging this cone along with it with a supersonic speed in this direction. So if you put an observer here, he will perceive the flow to approach with a supersonic speed from left to right. In addition, you will also see a component of the flow which is approaching him with the velocity equal to a from in this direction, because this cone itself is moving the observer this way, normal to the direction. So he will observe the flow to be approaching him in this direction with the velocity a. So the observer sees two components, one velocity u in the horizontal direction, another one velocity a in this direction. We will make use of this information later on when we look at flow deflection as the flow passes through the Mach wave. Okay. So the normal component of velocity is a, the speed of sound of the approaching flow. Now if I look at a situation like this, so let us look at a convex corner. We have already seen a sharp corner, now we are going to see a smooth corner. So let us say that we have a flow situation like this. So we have supersonic flow approaching a smooth corner like this. Okay, this is a smooth convex corner. Earlier we saw a sharp concave corner, now we are looking at a smooth concave corner. Now as the flow goes through this corner, what happens, because we have a smooth corner, is that I can imagine, let us say that the turning starts from here to here. Let us say this is the corner. Turning starts from this point and ends at the other point. Then I can actually imagine the corner being divided into many small infinitesimal number of infinite number of pieces, many small pieces. Okay, and each one of this little tiny piece deflects the flow by a small amount and acts as the disturbance that we saw in the previous case. Okay, so each one of those tiny piece of the wall is what we have described here as a disturbance. So each one of the tiny piece causes a disturbance in the flow and deflects the flow by a small angle, which means that I should be able to see a Mach cone from each one of this tiny piece. Okay, so I am going to draw starting from here. So each one should generate a Mach wave like this. Okay. Now the question is, are these waves going to be parallel to each other, or will the waves intersect, or will the waves diverge from each other? That is the next question that we must answer. I have just drawn it without looking into that effect. Now if you see, we defined the Mach number to be, we defined the Mach angle to be arc sine 1 over m. So when m is equal to 1, the Mach angle is 90. So as m increases, what happens to the Mach angle? This angle, the Mach, as m increases, the Mach angle decreases. As m increases, the Mach angle, right? So as m increases, the Mach angle decreases, correct? And as m decreases, the Mach angle increases, correct? So this is a concave corner, this is a compression corner, which means the Mach number is decreasing. So that means the Mach angle from each one of these pieces is going to increase. So that means the waves are actually going to, it is not going to look like this, the waves are actually going to intersect. And normally the way this happens is, so here is our first wave, here is our next wave. So this is how the waves normally do. So they actually intersect at a point. I am not going to show this, but that is what happens. So these are Mach waves. I have shown only a finite number, but what you must remember is the reason for discussing the earlier theory. The reason for discussing this theory, propagation of a disturbance, is to bring out the fact that any small point disturbance will do this in the supersonic flow. And we are actually saying that when you want to turn, each one of this little surface is going to act like a point disturbance. That is why I keep emphasizing point disturbance. So the flow, if you look at a streamline, so the flow goes through, then is deflected through an angle theta. Right? So here, so let us, if I call this m1, so m2 is going to be less than, m2 is going to be less than m1, probably greater than 1 in a corner like this. But the interesting point is, as these Mach waves focus at a certain point, they all coalesce, and from this point onwards we have so the waves coalesce and turn into an oblique shock. So a flow that goes through like this will go like this. Okay. So at this point, each one of this wave turns the flow through an infinitesimal angle, but when they focus and coalesce like this, then the turning is actually through a finite angle. That is why they coalesce into an oblique shock wave, because oblique shock wave represents turning through a finite angle, whereas Mach wave represents turning through an infinitesimal angle. So they coalesce and then do this. But notice that the process that the fluid undergoes when it goes through an oblique shock wave is an irreversible process. So in this case, S2 is if I say this is S1, then S2 is greater than S1. Whereas here the Mach wave, compression through a Mach wave represents an isentropic process. So here S2 is equal to S1. So if this is S1, S2 is equal to S1, which means that in this case we are going to get a slip line. A slip line which represents a discontinuity in some of the properties that we talked about earlier, okay, entropy particularly and other properties. Now, if I actually decrease the radius of curvature of this corner, as I keep reducing the radius of curvature of this corner, this point keeps moving towards the corner, and eventually when it becomes a sharp corner, we will have an attached oblique shock. Right? We have an attached oblique shock. Let us look at this picture. So you can see the situation sketched here. Notice that this is the supersonic flow. Here we have a smooth corner, and you see the coalescence of the Mach waves into an oblique shock with a slip line. Remember, the Mach angle, again, like the shock angle, the flow deflection angle and the wave angle in an oblique shock, the Mach angle is also measured with respect to velocity vector u1, or the velocity vector before the shock wave, so that this angle here is mu1, this angle is mu2, not the angle with the horizontal, but this is mu2 now, this is mu3, this is mu4. Okay? And given the fact that the angle increases with Mach number and the flow itself is continuously being deflected, that is why these waves focus to a point. Okay? So this is flow turning through a convex corner. Let us look at flow turning in a this is a concave corner. Please make this change. This is a concave corner, not a convex corner. So this is a supersonic flow turning in a concave corner. Next, we are going to look at supersonic flow turning in a convex corner. Yeah.
Flow passing through oblique shock will have higher pressure downstream of shock, and flow passing through isentropic compression will have less pressure. But about slip line, pressure should be same.
No, here in this case you cannot say that the pressure after the oblique shock is higher, because the oblique shock is a coalescence of all these Mach waves. So whatever pressure rise you are seeing across all the Mach waves at the end will be the same pressure rise. The strength of the oblique shock is such that that is what you are going to see. Okay? So if you look at this, you can see that the wave angle here, the wave angle is such that the pressure here and the pressure here are the same. The Mach angle, the Mach number is the same. Flow deflection is through the same theta, but then you are actually adjusting this to get a shock wave whose strength is such that the pressures are the same.
How can we make sure that angle will also, deflection angle is also same and pressure rise is also same?
We cannot make sure of that. We cannot make sure of that, but the flow, that is the solution that the flow will always go towards. That you are going to get a flow where the pressure is the same across this, but not necessarily the other flow properties. So there will be some mismatch. So the mismatch shows up in the other properties, but not in pressure. The flow will always evolve in such a way that the pressures are matched. Okay? There will be a mismatch in velocity, for example. Mach number. See, Mach number downstream of this need not be the same as Mach number downstream of this. Okay? We are not trying to say that everything will be the same. We cannot say everything will be the same. Obviously, entropy is not the same. So there will be some other quantities which are different. For example, there is a loss of stagnation pressure across the wave. There is no loss of stagnation pressure here, which means that if the static pressures are the same here and here, that tells me that the velocities have to be different. They cannot be the same. So the mismatch will show up, okay, not in pressure but in other quantities. So here we are looking at flow turning through a convex corner. And once again, if this is the part where the flow turning takes place, where the flow is continuously being turned. So, there is no turning in this section and there is no turning in this section. We have flow turning only between these 2 points. So, each one of this is going to act as a infinitesimal disturbance in the flow, and it is going to generate a Mach wave. Each one of this will generate a Mach wave, but in this case, because we are turning through a convex corner, the Mach number continuously increases. So, given the variation of the Mach angle with the Mach number, this tells me that the Mach waves are actually going to, the angle is going to reduce. So, that means if this wave from this part looks like this, a wave from the next part would actually look like this. So, there is no possibility of the waves focusing on each other and coalescing into an expansion shock. Okay. So, each one of this will generate a wave which looks like this. So, this is an expansion fan. So, this is an expansion fan and the flow is expanded through this, and the Mach number here, if you call this M2, M2 is greater than M1 in this case. This is an expansion process. And you may recall that whatever we are doing now, it is actually comforting to know that this trend is consistent with what we discussed earlier when we said that there is no counterpart of an oblique shock wave. In other words, you do not have an oblique expansion wave where flow is turned through a finite angle, because we said that would result in reduction in entropy or decrease in entropy, which is again second law of thermodynamics. What is interesting is this trend also tells us the same thing. It is this trend where we say Mach number, as Mach number increases, mu decreases. It is that trend which tells me that these waves cannot coalesce into an expansion shock like this. So, we are now looking at the same phenomenon, but from 2 different perspectives. In the first case, we said that there can be no expansion shock from second law of thermodynamics arguments. Now, we are saying that there can be no expansion shock based on considerations of isentropic expansion. Okay. So, it is very nice when different looking from different aspects, the concepts that we are discussing are consistent. Okay. That shows that everything hangs together nicely, everything works nicely. So, in this case, we said that as I reduce the radius of curvature, the oblique shock keeps moving towards the corner, and eventually when I have 0 radius of curvature for the corner, it will anchor itself at the corner here. A similar kind of situation here is something like this. So, if I have a sharp corner, so I have flow coming in like this, M1 greater than 1, and I have a sharp corner, M2 greater than M1. Then what happens in this case is this corner actually triggers an expansion fan. So, we have an expansion fan like this, and then the flow is deflected through this fan as it goes around the corner. So, even this expansion process is not accomplished with a single expansion fan, but with multiple expansion fans. Again, that is consistent, because if I accomplish this expansion with a single expansion fan, that means I am turning the flow through a finite angle, which means this would have been an expansion shock, which is not permitted. So, even this kind of turning has to be accomplished through a series of expansion fans, each one turning the flow through an infinitesimal angle. The only difference between this and the oblique shock is that the Prandtl Meyer wave or the Mach wave can represent both a compressive and an expansive solution. So, if the flow decelerates, then the Mach waves represent a compressive solution, right. If the flow accelerates, then the Mach waves represent an expansive solution. So, both are possible. So, when we derive expressions for connecting the Mach number and the flow turning, we must take this into account. So, let us write it down. So, Mach waves can be compressive and expansive. In fact, the earlier situation that we drew when we looked at a point disturbance which was traveling with supersonic speed, that was traveling with a constant supersonic speed. But if it starts accelerating, then we are going to generate different Mach cones. So, if it starts accelerating, then the Mach waves that it would generate would look like this. The same point disturbance, if it starts accelerating, then we will get different Mach cones like this. The same point disturbance, if it starts decelerating, then we will get Mach waves which look like this. Okay, which is why we are saying that Mach waves can be both compressive and expansive. Yeah.
In concave corner, flow downstream of both shock and this isentropic compression, flow is parallel to surface. And slip line should also be parallel to surface, na?
Slip line usually will be parallel to the surface, but there can be situations where you actually, instead of getting one slip line, you can also get maybe one more slip line. There can be more discontinuities. You can also get, in certain situations, slip lines like this. So, there is a discontinuity across each one of this and then it comes out like this. So, the exact orientation of the slip line depends upon many other quantities. So, that is not something that we can predict from the theory that we are discussing here, from the framework that we are talking about. So, what we are going to do next is discuss solutions to this problem, which were first proposed by Prandtl and Meyer. So, what we are going to look at, the solutions that we are going to derive is that each Mach wave, so the important aspects are that Mach wave deflects the flow through a infinitesimally small angle. And Mach waves are seen only in supersonic flows. And as we just wrote down, Mach waves can be compressive or expansive. And fourth point, the process is isentropic. So, what we are going to do next, or what this Prandtl Meyer solution does, is it relates the flow deflection angle to the Mach number that satisfies these constraints. That is what we are going to do next. Remember, for the oblique shock, we said that there were three parameters: Mach number, flow deflection angle and wave angle. But the advantage here is that the wave angle, we already know the relationship between the wave angle and the Mach number, because mu is nothing but sin inverse 1 over m. So, which means that we need to relate only the Mach number and the flow deflection angle, right. That is what we are going to do next. That is what the Prandtl Meyer solution does, with the additional condition that the process should be an isentropic process. Okay. Okay, let us see. What I am going to do next is, you have to follow this very carefully. I am going to take one such wave from a compressive solution, okay, and one such wave from an expansive solution, and draw the velocity triangles before and after. Okay. So, we are going to use the same orientation and draw this. Let us do this very carefully. So let me call this, this is the direction, let me call this region 1 and region 2. Let us call this U1. This is normal to the wave. And what did we say earlier about the normal component? The normal component is equal to the speed of sound, correct? So this is the normal component and this is equal to A1. This is the tangential component UT. And this angle is the wave angle mu1, correct? So as I said, the observer sees two components, one U1 and another one normal to the wave. That is what we have sketched here. Let us mark these points. I am going to mark this point as O and I am going to mark this point as P. This is not the same triangle as earlier, okay? This is a different triangle. O and P are different from our earlier triangle. Now this is a compressive wave. So after passing through the wave, the normal component of the velocity decreases, just like in an oblique shock, right? So the normal component decreases. So I am going to show that like this. So this is the normal component. This was the normal component before. This is the normal component now. So this has become smaller. So I am going to call this UN2. The tangential component remains the same as earlier. And so U2, the new velocity vector, looks like this. And the flow was actually like this, the velocity vector was like this before the wave, and now after passing through, the velocity vector has deflected, and this angle, we will denote this angle, this is the flow deflection angle, and we will denote that angle as d nu. That is the flow deflection angle, and we are denoting it explicitly with a differential to indicate that each Mach wave deflects the flow through an infinitesimally small angle. Okay? Remember, the solution must satisfy these constraints. Okay? So the deflection angle has to be infinitesimally small, and we will use this fact also later on. For now, we have shown it as d nu to indicate that it is infinitesimally small. Later on, we will actually make use of the fact in our mathematical derivation also. So this is the compressive wave solution. And let me label the vertices like this. So let me call this O and let me call this vertex R. Okay? Any questions? Yeah.
What exactly is difference between this and oblique shock?
I am going to show that in a minute. The difference is this is d nu, and I will make use of that. There are two differences. Number one, this is equal to speed of sound, which was not true before, right? And number two, this angle is very small. How are we using that fact? We will use that fact when we go through the mathematical derivation. Okay? For example, you can probably guess that sine of d nu is, what is it going to be if d nu is very small? D nu itself. That I will use later on. Okay?
Mn1 will be 1 in this case.
Mn1 is 1 in this case, correct? Yeah.
This normal component, normal Mach number is 1.
And that is correct, because we are saying this is an this is like an acoustic wave, right? Mn1 should be 1 for an acoustic wave. It's consistent. That's correct. And if Mn1 is 1, what would be the strength of the shock wave? 0, infinitesimally weak. That is exactly what this wave is. So that is perfect, right? Now let us look at the expansive solution. So I am going to take one of this wave and then draw this diagram like this. Same diagram on the left hand side, but different on the right hand side. So So this is region 1, this is region 2. So this is UN1, which is equal to A1, this is UT, this is U1, this angle is mu1, and as before we will label this vertex as O and label this vertex as P. These are supposed to be the same, okay. This is the best I can draw. I will show you the actual picture after we finish this. Now after passing through the wave, this is an expansive solution, so let me write it here. This is an expansive solution. So after passing through the wave, UN1 increases, right. So this is UN2 now, this is UT and this is U2. So now as a result of UN2 increasing, the flow has been deflected away from the wave through an angle d nu, okay. So in the earlier case, the flow was deflected towards the wave through an angle d nu, it was a compressive solution. Now the flow is deflected away from the wave through an angle d nu. And let us label this vertices same as before, O and R. Okay, any questions so far? Alright, now what we are going to do is combine these velocity triangles. So what I am going to do now is, I am going to take this velocity triangle and notice that this is the same as this. So I am going to take this side and make it coincide with this side. So I am going to combine these two into a single triangle for this solution. I am going to do the same thing for this solution also and draw a composite triangle, right. Let us do that. I am enlarging this so that things are clear, okay. I am not drawing it to the same size as the other one. I am enlarging it so that things will become very clear. So this is O, this is P, this is UN1, the arrows are not required, I think we should be alright without the arrows. So UN1 equal to A1, this is the triangle before the flow and the triangle afterwards looks like this. This is UN2, this angle is mu1, this angle is d nu, correct. Notice that I have taken the second triangle, pasted it here, okay, and this angle is going to be mu1 minus d nu. And okay, so we have OR, so this is point R this is vertex R, and so OR is equal to, let me write this explicitly here, OP is equal to U1, OR is equal to U2. Now let me do the following. This is 90 degrees. Let me do this geometric construction. I have extended OR up to Q and I have dropped a perpendicular from here to that. Now notice that if you look at this triangle, right, this is UN2, right? This whole thing is UN1. So this PR is nothing but UN1 minus UN2. So I can actually write this as DUN because we expect the change to be very small. So what we are saying is UN2 is equal to UN1 minus DUN. That is what we have done here. Okay. Similarly, if you look at this is U2, OR is U2. Now if d nu is a small angle, here is where we are going to make use of the fact that d nu is small. If d nu is a small angle, then OP is approximately equal to OQ, correct? For small d nu, much less than 1, OP equal to U1 is approximately equal to OQ, which means that since OR is U2, RQ is going to be DU, right? OQ is equal to U1. So this whole thing is U1, this is U2, so this is going to be the change in velocity, DU. So I can write U2 is equal to U1 minus DU for this solution. Okay, so now we are making use of the fact that this is small, unlike the oblique shock solution. I am going to do the same thing for the expansive solution also, combine the two triangles. Let us do that. We do this slightly like this. So this is supposed to be along the same line, okay? So this is our OR, this is U2, and now what I am going to do is do the same construction as before. Call this point Q, let me call this point, let me write this over here. So I call that point Q. Now this whole thing, remember, this whole thing was U2, this is my flow deflection angle d nu, this angle is mu1. Now I use the same trick as I did before. I notice that UN2 is going to be UN1 plus DUN, right? UN2 is equal to UN1 plus DUN, and so let me write that down. DUN. Now if then OP equal to U1 is approximately equal to OQ, right. So, this whole thing is U1, and if d nu is very small, then OQ is also going to be U1. So, U2 is going to be U1 plus du. Okay. Now, you can see that I have kind of brought both these solutions into the same framework, except for, so here the angle is mu1 plus d nu, this angle, here that angle is mu1 minus d nu, here this is un2 is un1 minus du1, here it is plus du1. So, with the plus minus I have brought both this into the common, into a same framework. Let us look at these triangles done in a neat way. Is yeah, here it is. So, you can see the same construction 1 and 2, right. This is the velocity vector before un1 equal to a1 ut. This wave angle is the Mach angle mu1, and after passing through un2 decreases, is less than un1. So, the velocity vector shifts that way because ut is the same. This angle is d nu, and I have combined these two triangles by merging these two sides like this. Right, and you see the same construction. So, U2 is U1 minus du, and we have made use of the fact that OP and OQ are the same because d nu is small. We have done the same thing here, combined these two triangles, but the flow is deflected away from the wave, combine these two and use the fact that OP equal to OQ equal to U1 because d nu is small. Okay. Alright, so now we are ready to pursue the solution to this equation. Let us get started. We will not be able to complete this today, but let us get started. So, we can write in the general case for the Prandtl Meyer solution or for the compression or expansive solution, U1 is U2 is equal to U1 plus minus du, and UN2 is equal to UN1 plus minus dun. So, from triangle OPQ, PQ is equal to U1 sin d nu, OPQ in both the cases. PQ is equal to U1 sin d nu, and for small values of d nu I can approximate this as U1 times d nu. Now, angle or PQ is equal to mu1 plus minus d nu so that from triangle PQR we get PQ is equal to dun times cosine mu1 plus minus d nu, and for small values of d nu this can be approximated as dun cosine mu1 itself for small values of d nu. Right. So, we are making use of the fact that d nu is very small in this case, and we are making use of the fact that d nu is very small here also. So, we have two expressions for PQ, and if you equate these two expressions for PQ, we have one expression for PQ here, another one there, and if you equate these two expressions we get d nu is equal to dun divided by u1 times cosine mu 1. Remember, we are trying to relate the flow deflection angle to the Mach number. The wave angle itself is already known in terms of the Mach number. So, that is where we are going with this. So, we will continue with this expression and try to, this is a function only of Mach number. Okay. So, I need to make sure that I rewrite this also in terms of Mach number, and then we will go from there. Okay. This we will pick up in the next class.